Hey everybody, this is Larry. This is day 13 Yeah, day 13 of the legal day. Challenge the like button, subscribe, and join me on Discord. Let me know what you think about today's farm. Today, my foot's still in the cast. Nothing has changed there. I did do a 5K walk. Mostly non-stop. I did stop for dumplings. So I don't know if that counts as like a bit, but still. So hopefully I'm making progress. I don't know. I do try to I wouldn't say I try to run, but I try to take a few jogging steps, and now it's still no bueno. So it's a little bit sad. I feel like I'm losing fitness so much, but it is what it is. Sometimes you just gotta do what life gives you, right? Anyway, all right, let's take a look at today's farm. We have 3066 minimum operations to exceed threshold YU2 medium farm. Hope everyone's having a great week. As good a week as you can have. And yeah, let's see. In one operation, you will, you have an index, or you have an array, 0 index, integer k. In one operation, you can take the two smallest number, not a choice. Remember, that's one thing that you, I think when you read these poems, the language kind of matters, right? And I haven't finished reading this yet, but what I want to point out that as I'm reading this is I'm like, okay, in one operation you will do these three things, and there's no choice, right? Meaning you don't get to choose X or Y or whatever. You just do it, right? So in my mind, immediately I'm thinking about like, okay, then maybe heap. I mean, I don't know yet because I haven't read. Actually, I haven't even read the other farm, the other operations yet. But that's the immediate in my mind. It's like, okay, maybe it's heap, right? Because we have to repeatedly take the smallest number, so something like that. Okay, so we take the two smallest number, we remove it, we add anywhere in the array. I don't know what add anywhere in the array means. Minimum number of arrays, so that. Yeah, I mean anywhere in the array is just misleading because the order doesn't matter for future operations, right? So it doesn't matter. Again, like I said, there are no choices, right? So you just got to simulate. The only thing that may concern me is that k could be really big, maybe. Then obviously you have to figure out a smarter way. Let's take a look. And k is indeed 10 to the 9, so that is actually really big. So you can't just simulate, right? So that's kind of well, right? Oh wait, no, I misread this. K is not the number of operations. K is just this formula, or like when order. Do you return -1 if you can't? Or oh wait. Okay, I see. But I mean, like I said, there are no choices. So you just keep on doing this, right? I mean, that's it. For a second, I thought k would be really big, as in maybe there's a lot of operations that you have to do or something like that. But now that I think about it, I don't know what I was interpreting. But yeah, no, I mean there are no choices, so you just simulate. Everything's just simulate, right? And you may say, well, if k is really big, can it be 1 in infinite, right? Like, or time limit exceeded or whatever, because k is really big. Well, that comes from analyzing this, and it just comes from 2 times min max, right? And you can kind of think about this with the smallest number possible, which is ones, right? So if it's going to go 1, then and I did this in my head, but I just want to write it out. So if you have 2 numbers, you have 1 1. Let's just say you have a million ones, right, for the purpose. Then now, after 1 iteration, then you remove 2 ones and replace them with a 3, right? Okay. And then now, let's say you have infinite number of 3s. You combine a lot of 1s, they become 3s. Then what? And then now, it's just 9, right? Let me start every time you do this in the worst case scenario. Well, one is that you're gonna lose half the numbers. So even if n is a million, you can only do this like 30 times, right? Or whatever, 20? Yeah, 20 times because it doubles. Yeah, you lose half the number, half. So you go only 20 times. And actually the summation is, of course, 1 million. If you had a million numbers, 1 million plus 500,000 plus 250,000 plus ... right? So in that case, assuming it's I mean, technically, you know, there's some nuances there as well with respect to the cost, but given it, you know, pretending for now that's all one, then that means that just takes actually 2 million operations, right? So very reasonable, very fast, and that's in the worst case, with only that in mind, nothing else, right? So yeah, number one is that you lose half the number every time. The other thing is that the numbers grow exponentially. So that means that if k is big enough, like if k is 10 to the 9, is it, or whatever, and you multiply it by 3 every time, that's going to be a log 3 number, right? I don't know what log 3 of 10 to the 9 is, but even log 2 would be just 30, so I don't know, right? 20 something, say 20 is an upper bound, maybe. I don't know, I can't do math. I don't know log 3s on my head, but right, so that's gonna be fast enough, is my point. So that these things together suggests is that, okay, now we simulate. I don't know if that was too easy for you, or like, you know, you're like, but Larry, why are you explaining so much? It's because, I don't know, every time I explain it too little, people complain that I don't go over some of the details, and sometimes when I don't go over the details, or when I do go over the details, people are like, oh, this is easy, you didn't need to explain all this, and I'm like, dude. You know, come on. It is what it is. but yeah, so it is what it is. But hopefully that makes sense, though, in terms of just analysis of, you know, why this is fast enough. And of course, I do this before writing my attempts, because that's what you're supposed to do, really, right? But yeah, okay. So yeah, let's do it. And the insert anyway doesn't make a difference, because it's still just going to be, you know, whatever. So we want a heap, right? So we heapified nums, and then while length of nums is greater than or equal to 2, we go xy, and x should be the min. Oh no, well, it's actually, I don't know why I would like that, but right. So x being the first number to pop will be the min, at least in Python, right? Because it is a min heap. So then now we can just do x plus 2 plus y, right? Is equal to and then we put it back in, right? So one thing is that, okay, we should check the beginning, the top of the heap, right? So if the top of the heap is greater than or equal to k, then we break, right? Because if the smallest number is greater than or equal to k, that means all the numbers are greater than or equal to k. And we can also just count for the number of operations, right? So count is equal to 0. Right? So okay, yeah, actually we couldn't even just return then, right? We could just return count, because then now here, if the loop ends, that means there's only one element left, and they're not bigger than k, so then we can just return -1, right? Oh wait, they say that it's always guaranteed. Okay, well, I suppose so. I mean, I guess we'll return -1 anyway, but whatever, right? Oh no. Did I misunderstand? Did I misunderstand this? Huh. Well, let's take a look. Maybe I misunderstood this. Okay, so that's a heap. You take the 1 and the 1, and then you put in the 3, right? And then next, you do 2 and the 3. Oh, number 1 is right. Okay, that's why I was like looking at example 1. I'm like, that the numbers aren't even right. Okay. 2, 4, 9, 3. Okay. After 2 operations, 15, 9. Oh wow, that is actually a bad edge case by me. Because basically, yeah, this one returned false before this is returned true. So I guess we have to add a thing here first. Wow, I don't know why I didn't catch that. Well, or the why is that I'm dumb, but I don't know if it happens, I suppose. All right, let's give it a submit. I mean, other than that, I think we're pretty confident about it. We did the proof and stuff. I just kind of, I just did the if statements clearly not in a great order. But yeah. Yeah, that's it. So this loop, as I said, right, this loop, every time it halves, so this is gonna do log n, or I guess O of n iterations, right? Because as we said, the first time it's going to be O of n, or the first time it's going to be n numbers or n iterations. Second time it's going to be log n iterations, and so forth. Oh, sorry, man, I am saying it wrong. N plus n over 2 plus n over 4 dot dot dot. So this is going to be O of n iterations because it converges to 2n iterations, right? And each iteration does log n work. I mean that's not a tight bound, obviously, in the sense that you know, even the heap gets smaller, so like it starts with log n and then log n minus 1 and log n minus 2 all the way I actually don't know what that sums to be frank. But for now, let's just say it's n log n, and maybe I'll spend like a second n log n time, right? Because everything is log n inside per se. All right, let's see what I'm curious, so I'm gonna ask ChatGPT. So that is one thing that it is good at, maybe. What does log n plus log n minus 1 plus log, maybe I could say log, what does the sum of log I from I, or for I from 0 to n equal to? The sum you're asking for. Okay, it does print the sum. Log 0 is undefined. Okay, fine. We do not mean to log. Oh, I asked it to be in 0. So the sum is log of n factorial. I mean, that's right, but can you simplify log n factorial? Oh, Stirling's approximation, that's right. I actually didn't know this one. But I thought it looked familiar, but I'm just not really. Is that right? Well, oh, I see. It's the summation of it. Not the, so anyway, it's n log n, it's the TLDR. It seems like the summation of all that is, and technically it would go, because first, yeah, so I guess it's n log n anyway. So maybe I did know that in the past and I just forgotten about it. So yeah. Anyway, sorry for that. But basically the proof that they're saying is that yeah, log 1 plus log 2 plus log 3 plus log 4 plus dot 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 log n, right? So that's going to be sum of log I from or the identity they said was that log A plus log B is equal to log of A times B, which is true. I mean, yeah. And so this is just going to be equal to log of n factorial, which thanks to Stirling's approximation is n log n, right? And of course, in this case, we're actually summing all the stuff that's inside. So so n log n is amortized out. You don't even have to count this loop because we just literally do all the sum, right? Because actually, I mean, I said that this is 2n, which is an upper bound, just for me to be like, okay, well, look, there's an upper bound, right? But actually, I guess the easier invariant is that every time you do this loop, you have one fewer item. So that's actually a better bound, and maybe I messed up on that analysis, to be frank. I just, the reason why I did that earlier was that I just wanted to establish an upper bound for me. And that is a good enough upper bound for me to implement. But it's not a tight upper bound, right? That's what I mean. And here, now, the other invariant of that, every time you do this loop, it is one fewer items, is actually a better bound, right? So, okay. I would also say, so that means that this loop's actually all of n times, so that's kind of nice. But I didn't know this proof. I mean, I didn't know this proof, but maybe from like a decade ago or something. So it's kind of nice to remember. I just thought that, or rather, I thought that the bound was not, like, I knew that it was n log n, but I didn't think it was a, I didn't think that was a tight bound, if that makes sense. Like, I thought maybe there's a lower over big O that, you know, that still has n log n as the big O, but you know, it's almost saying like, if that doesn't make sense to you, it's almost saying that, oh, I know this is O of n cubed in the sense that it could be n square, but it's you know, it's at worst n cubed as a proof, and you're like, okay, well, n cubed is fast enough. I don't care if this is n square or n cubed, right? So that's basically my idea of thinking about this for n log n, but I didn't know that that was a tight bound as well on the other side, on the summation. So I guess that's interesting, actually. Okay, yeah, so I learned something today as well. Thanks for watching. That's all I have. Hope y'all enjoy the rest of the week. And yeah, stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye-bye.